The network plays a key role in AI model and inference training. And on today's Tech Bytes podcast, sponsored by Nokia, we're going to talk about why you need a high performance network for AI training workloads. We'll also talk about essential technologies such as Rocky V2 and others that will make Ethernet suitable for scale out networking, the role of the Ultra Ethernet Consortium in driving a new Ethernet standard for AI and high performance computing, and what Nokia brings to the table in terms of hardware, software, and automation. Our guest is Alfred Nothaft, Senior Director of Product Management at Nokia. Alfred, welcome to the podcast. And just to get us started, what's the network's role in AI model training and inferencing, and how does network performance affect those outcomes?
Well, thank you. Thank you for having me. I would say that it's really during the training process that the network has the biggest impact on the overall performance of the training and AI workload. It's really during this period that you have a huge block of source data that
Hmm.
has to be distributed across a large number of GPUs. And then those GPUs have to start processing that information and ultimately coming up with a final result of the large language model.
Hmm.
Um, but I guess during that process, all of these GPUs go through a certain amount of processing. But then after each one of these iterations of processing, they have to share that information with each other.
Hmm.
And it's at this point where the network becomes key because it is ultimately the roadblock or
The bottleneck potentially.
the bottleneck to sort of all of the GPUs being able to restart and continue on with their processing. So it's really hugely critical that the network provides the fastest performance possible, and basically avoids any kind of congestion because that's basically holding up the process for the rest of for the next set of iterations.
Yeah, so one of the metrics I've heard about is something called job completion time, which in my understanding is, as you mentioned, once all of the GPUs complete their calculations, they have to share the results with all the other GPUs, and then nothing can happen until that final bit of information is communicated to the GPU and it does its processing. So that job completion time means you could have GPUs idle, and these things are expensive, and folks want that to happen as quickly as possible.
Absolutely, absolutely. And i- in this case, time is money. The
Mhm.
longer these GPUs are sort of sitting, waiting for the information to be shared and distributed across each one of the GPUs, they're sitting idle. So it's really critical that you avoid any kind of congestion and at the same time provide the highest amount of bandwidth and throughput through the network as a whole.
Mhm. So we're talking here specifically about Ethernet networks, and as everybody listening knows, Ethernet wasn't designed to be essentially a lossless network and may not be on its own well suited to meeting the demands of an AI network fabric, which doesn't want to have to deal with packets being dropped, retransmissions, and so on. So, what are some of the technologies that are being applied to Ethernet networks to make them better suited for these kind of workloads?
Yeah, I mean, I would say Ethernet has a huge advantage overall because of just the sheer amount of industry support that Ethernet can sort of bring to bear. The port speed increases year after year after year,
Hmm.
I mean, really, we see no end in sight in that regard. In addition, we have a large number of capabilities that have been built into Ethernet um, to support not just the bandwidth through the use of various load balancing mechanisms that we have. Um, Things like dynamic load balancing, flow-based load balancing, per packet type load balancing. So you have a lot of different tools to bring to bear to provide the GPUs the type of bandwidth that they need. But
Hmm.
then we also have a number of congestion avoidance and mitigation mechanisms that can help Ethernet kind of provide that lossless capability that the GPUs are looking for. When we say a lossless Ethernet fabric, really what we're trying to do is we're trying to make sure that those GPUs can exchange information efficiently.
Hmm.
And if there is congestion that starts to build, because you have a large number of GPUs and they're all wanting to largely send data between themselves at the same time. So
Hmm.
you're going to ultimately end up bringing congestion into the network just because of this sort of iteration based processing. So elements like ECN or Ethernet bleh.
Explicit congestion notification.
Yeah, thank you.
Yeah.
Explicit congestion notification and priority flow control, they kind of give you sort of that traffic cop capability into Ethernet, where ECN is kind of that warning light. Hey, you're going this speed, to try and give you a little bit of back pressure in order to have the sources slow down so you don't actually reach sort of true congestion environments.
Okay, so there's a signaling mechanism being used to tell a source, hey, maybe back off on transmitting for X number of microseconds or whatever.
That's right. So as the traffic is flowing through an Ethernet switch, if it starts to see a buildup of congestion or queue depth, then it can signal that traffic that there is congestion building.
Hmm.
This goes to the destination and then gets ultimately reflected back to the source. And the intention is the source actually slows down and throttles itself.
Hmm.
Now, if the congestion gets to the point where beyond just congestion and you actually start to fill buffers and potentially losing traffic, then you get into more of a more dramatic situation where PFC starts to kick in and actually starts to tell a switch or a source to actually pause altogether, at least for particular forwarding classes. And that's really kind of the worst case scenario, because now you're actually stopping traffic. But it's also an indicator that you've already lost traffic. And again, the key point about avoiding congestion and that traffic, that lossless Ethernet fabric, is if these GPUs go out of sync, then they basically have to back up to a fixed checkpoint or a saved checkpoint,
Hmm.
and then restart the processing over, which means you've lost data, you've lost time, and you've lost money.
Okay. So that's explicit congestion notification and priority flow control. Those are two of the techniques. I also mentioned Rocky V2 in my introduction, which stands for RDMA over Converged Ethernet version 2. Can you tell us a little bit about what that's bringing to the table?
Yeah, so Rocky V2 brings a mechanism that allows these GPUs to share blocks of data from their memory from one GPU to another very efficiently. So it's the overriding mechanism in which data is shared between the GPUs, in this sort of data block fashion.
So transmitting memory from sender A to receiver A without having to do like sort of walking through the OS of that device.
Right, because you don't want the GPUs themselves to have to worry about that. So
Hmm.
Rocky V2 gives the ability for the network interface card itself, the NIC, to send the data directly without involving the GPUs in that process.
Hmm. So we mentioned the Ultra Ethernet Consortium. They recently released their 1.0 specification, which again is intended to make Ethernet better suited for AI and HPC workloads. Can you talk about the specifications focus on things like scale-out networks and the transport layer?
So the UEC is looking to bring Ethernet networks into sort of the next generation of AI workloads. So it's really trying to focus on all of the different mechanisms. So, going back to the full stack of communications layers, it's really trying to look at all of the different layers themselves.
Hmm.
And one of them is, they came out with the UET, which is kind of a transport mechanism that largely lines up with the capabilities of Rocky V2. And again, allowing individual network elements to very efficiently share data from one node to the next,
Hmm.
or multiple nodes, as it were, as well. And then it also brings in the concepts of ECN and PFC, which we talked about just a moment ago.
Hmm.
Now, what it does is it starts to add additional layers into that. So an example is with ECN, the data is sent to the original packet that was experiencing the beginnings of congestion, are
Hmm.
sent to the destination and then reflected back. An ECN notification is sent back to the source. The ECN is trying to optimize that process by, instead of sending the original packet, as it actually sends a trimmed packet. And so this process is called packet trimming.
Mm.
And the whole purpose of that is to make the process of notifying the destination and ultimately the source of the congestion building as quickly as possible. So by shortening the packet, you can expedite that traffic through to the destination much faster, and at
Hmm.
a higher priority. So it's trying to enhance a number of different layers within the network to, again, make Ethernet even better for supporting these type of AI backend networks.
So there is now a 1.0 spec for UEC. Are Nokia switches UEC compliant?
Absolutely. We're 100% capable of efficiently forwarding ECN traffic today. We've actually been doing a number of testing in our lab to support, to validate this. And yeah, typically when we talk about the back-end networks, we would be utilizing a Nokia IXR H4 or H5 switch, and we've
Hmm.
been doing testing with ECN traffic for several weeks now since the release of the spec.
So one question I have is that, a lot of the switch hardware being used in AI networks is built around merchant silicon. So how does Nokia differentiate in regards to features and capabilities that it can bring to the table?
For AI backend networks, we would typically position the IXR H4 H5 switches. These switches, they have all of the capabilities that you would need for AI backend networks. Full ECN and PFC congestion control. We support um, standard load balancing mechanisms like flow-based, but also dynamic load balancing to more efficiently utilize all of the ECMP paths.
Hmm.
We're also bringing out per packet load balancing capabilities, and we'll continue to enhance those capabilities with packet trimming coming in the future. But I think additional layers of importance to the network is providing basically telemetry about what's going on in the
Hmm.
network.
Hmm.
So really providing streaming telemetry about ECN and PFC events, about buffer fill rates at a very high rate, to allow the network itself to be, or the management of the network to know that events like that are occurring and to try and mitigate them. And then, of course, there's the reliability of the software. Nokia has always been very focused on making sure that our network operating systems provide the highest reliability. And that's certainly true with SR Linux in support of these types of applications.
Yeah, telemetry is absolutely critical for these kinds of workloads again because of the high stakes around network performance here. So I can see how that would be key. What about automation for configuring and operating these AI networks?
Yeah, so we have a system called EDA, which provides the ability to automate and control these types of AI backend networks. This EDA can really automate and simplify the rollout of these networks. You can actually, by putting in a few parameters about the size of the network, the number of switches, and so forth, it can automate the actual configuration, the layout of the networks for you. and then monitor the network once it's actually deployed itself. So I
Mm,
think automation is huge because we're talking about networks with potentially um, hundreds, thousands, tens of thousands, going to millions of connections. So you have a large number of sort of moving parts. You have the switches, you have all the
right.
ports, and the optics themselves that you have to monitor. Automation, I think, is going to be key and just keep growing.
So, Alfred, I know we've had just a short time together. If folks are curious about what Nokia is up to with AI infrastructure, particularly on the switching side, where should they go to get more details?
Yeah, you can absolutely go to the Nokia website and look for the networking for AI workloads landing page. And from there, you can see a lot of information about products and solutions that Nokia can help with.
All right, so that's nokia.com, and then look for networking for AI workloads. We'll also have that specific link in the show notes that accompany this podcast. So thanks, Alfred, for being with us, and thanks to Nokia for being an ongoing sponsor of Packet Pushers. We really appreciate it. And if you, the listener, happen to reach out to Nokia, it would be a big help if you mentioned that Packet Pusher sent you. Speaking of Packet Pushers, check out our ever-growing roster of technical podcasts for your professional development on networking, security, IPv6, DevOps, and more, plus our industry blog, 2 weekly newsletters, our community Slack group that you can join, our YouTube channel, and an IRC group. Find everything at packetpushers.net. It's always free, no login required. You can also hear us on Spotify, thought lead with us on LinkedIn, and rate us on Apple Podcast if you would. Last but not least, remember that too much networking would never be enough.